One of you just asked a really great question again about kind of visualizing the difference between homogeneous and heterogeneous state graphs. So I thought I would just make a heterogeneous state graph version of the occasionally dishonest casino problem. So here on the left we have the homogeneous version that we've just been talking about. So it's got self-edges and transitions between the two possible states. And then here on the right, we've got what you might consider to be a heterogeneous state graph version. So you could imagine, you could think of this as basically being time 1, time 2, time 3, time 4, time 5, etc. Because you look at the directed edges, and you can see that once we leave time 1, we're in time 2, and we're never going to go back to time 1, right? Question?
Like saying, if in the next time step, or the next hour,
Right. So, absolutely. The only point of making this more complicated looking graph would be if we wanted to use different probabilities on these edges. If we were going to use just the exact same probabilities on these edges, we might as well just use the simpler homogeneous state graph. What this extra complication gives us is the ability to model different transition probabilities at different times. It might or it might not. I think you can see that if we're strictly trying to be heterogeneous at the different transition probabilities at every time, and we want to have infinite time, we're also going to have an infinite graph. Whereas, even just this simple homogeneous state graph can represent an infinite Markov chain. Great questions. Any other questions about this? Okay.